Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about, science and math. And today we are in AP Chemistry by the College Board units, Unit 3. My other video that says Unit 3 is by the AP textbook. So we are finishing up the first part of the notes in Unit 3, 1 through 6. And what we did first is we looked at how you can rearrange an equation for something else. I ended the last video on my soapbox saying that you should always use your equations straight. Don't move them around. Use them, put the numbers in, then move them around. But then I had to go and be humble, because AP will sometimes give you a problem with no numbers, and you have to do this. And we can do it. We can take it in stride, and it's really kind of fun because it's math. So we were able to use PV equals nRT, solve for V, density equals mass over volume, so we substituted what we solved for into the denominator. Then the molarity is mass over number of moles, mass number of moles. We took that out and put the M in for it instead. And then pressure was in the denominator. And in math, if something's in the denominator of the denominator, it gets to move up to the numerator. So then we got the equation we were supposed to have, D equals MP over RT. All right, I had to do that twice because the video didn't work, because I had a big fat video on it from yesterday and had not deleted it. All right, so now we were to this one, and this is an AP problem where it says the density of dry air at STP is 129 grams per 1 liter. What is the density of dry air at 100 degrees Celsius, assuming that pressure remains at 1 atmosphere? And so we know to change, we always have to change Celsius to Kelvin, so we added 273 and changed that one to Kelvin. Our original problem, our original thing is an STP. STP is 273 Kelvin in 1 atmosphere. So first of all, we need volume, because we're going to need our new volume so we can figure out our new density. So we use Charles's law, V1 over T1 equals V2 over T2. Our original volume was 1 liter. This is grams per 1 liter. That's where that 1 came from. 273 is our original temperature. X is our new volume. We don't know it. And then our new temperature is 373. We cross multiply, solve for X, and we get our new volume. Now we can put it into our density equation to get our new density. Our mass stays the same. The atoms have not gone anywhere. Those grams are still there. We just have a new volume. So our new density, we just divide, is 0.94 grams per liter. Everybody good? Heard it twice. That should make it like extra good, knowing this thing. Okay, so now we always in AP, they like those follow-up questions. So does this make sense? Is this logical based on what we know about hot air balloons? Well, our old density was 1.29. Our new density is 0.94, which is greater. Our first one, right? Wouldn't you rather have $1.29 than 94 cents? Of course you would. So this is greater. Pac-Man wants to eat the bigger one. So does this make sense? Yes or no? Yes, I saw some yes little nods there, because hot air is less dense than cold air, right? That's why hot air balloons rise. It's kind of fun, isn't it, seeing it mathematically? Okay, so this is a real AP question from 2009. The only thing I noticed about this is we were told that AP only uses atmospheres for pressure, and this one uses torr. So it's old, it's from before y'all were born, so that must be something they have changed over the years, okay? So it's multi-part, and I want you to make sure that you can just sort of follow my logic, how I'm gonna do it. A student was assigned a task of determining the molar mass of an unknown gas. The student measured the mass of a sealed 843 milliliter rigid flask that contained dry air. The student then flushed the flask with the unknown gas and resealed it and measured the mass again. both the air and the unknown gas were 23 degrees and 750 torr. That's the torr thing. The data for the experiment is shown here. Now, he messes up. Anybody have an idea what he should have done that he didn't do? What did he do wrong? He messed up. He did not get the mass of the empty flask. He should have weighed it first, because later he's going to want to know the mass of the gas, and all he's going to be able to have is the flask and the gas, and he can't subtract the flask. But if he had done that, this whole thing would have been a whole lot easier, okay? So just know that he messed up, but he's going to salvage his experiment with math. Sometimes you can do that. Sometimes you can get out of the situation with math. Okay, so calculate the mass in grams of the dry air that was in the sealed flask. Okay, so what he could have done was weighed it together, then like let it out or something. Okay, the density of dry air is 1.18 grams liters to the -1 power. Okay, so a lot of times on the AP test, they'll do things in an unusual way just to try to make you panic. You look at that and go, I don't even know what that means. Why is liter to the -1? This doesn't make any sense. What does that mean, that liters to the -1? Does anybody know that in math? Oh, I see y'all saying no. That makes me happy because I get to teach you something. That is symbolism for liter is in the denominator. This is exactly the same thing, grams per liter. Just confusing. Why would you do that? No good reason. It's harder to do on the typewriter. It's easier to just go slash it, capital L. But the reason why they did that was to confuse you. So now you won't be confused. You've seen it. So this is 1.18 grams per liter at 23 degrees Celsius and 754. So that's our density. That's what we know. And we need to get our mass. So we've got the volume, 843 milliliters, and we can get mass because we know grams per liter. We can cross out our liters and solve for grams. Now, it bothered Elisha first period that I was a little lazy and didn't change this to liters before I wrote it down. Do you see my laziness? But I was just lazy. I put it in my calculator right, and I switched it to, I moved my decimal point, and I marked out my liters, and I got grams. So, forgive my laziness, okay? I shouldn't have done it. I repent, but I did, okay? So just know, whoop, 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 you gotta move your decimal point before you multiply, and then you'll get 0.995 grams of air, okay? All right, everybody good? You promised I didn't confuse you too bad by not converting to liters first. You can do it. Convert it to liters, then do your math. And then your liters will cancel out. So we did the first part of the problem. Now, how they did the free response on the AP test is you have a question and then you have part 1, part 2, part 3, usually about 5 or 6 parts to it. And it doesn't go from easy to hard. It's just random. It'll be a hard part, then an easy part. And if you can't do a hard part, you make something up and just continue that number on into the easy part. And they'll give you full credit. They'll just take off for the part you didn't do. Okay, now calculate the mass in grams of the sealed flask itself if it had no air in it. Well, we've got the mass in our data table of the flask and the air, and now we have the air, so we subtract and we can get just the flask. That's what we should have done before we got started. We wouldn't have to have done this math, right? If we had been a little better in our lab techniques. Okay, now calculate the mass in grams of the unknown gas that was added to the sealed flask, okay? So we got from our data table the flask plus the unknown, and we can subtract just the flask and we can get our new mass. Do you see how these are easier than that was? It went a little hard, easy, easy. Do you see that? Okay. All right, so everybody good so far? You don't have to write anything, you just have to listen. I ran this off for you. Okay, using the information above, now figure out the molar mass of the unknown gas. So we use PV equals nRT. They gave us the pressure of 750 torr. Here I was a good girl and converted to liters, 0.843 liters, because it has to be in liters. N is what we're looking for. This is the R for torr. So, this is just a given, a constant, you will be using the other one on the test. But this would be like giving them the problem if not. And then that was our temperature. So we solve for N. We multiply these together, then divide by 62.36, enter, and then divide by 296 Kelvin, enter, and that's N. Okay, next, but that's not what they asked for. They wanted the molar mass. So the molar mass is grams per mole. So we take our grams that we had gotten previously and divide it by the number of moles, and we can get the molar mass of our unknown gas, 40 grams per mole. How do you feel about that? Kind of follow it? Okay, next. They said, what if you find out that your unknown gas was really carbon dioxide that has a molar mass of 44 grams per mole? What's your error? We have been doing this since honors chem, haven't we? All it is you take the absolute value of the difference, divide it by the right answer, times 100. So it was 9.1% error. Everybody remember that from honors? We did that first with our metric Olympics. We started figuring out error. Okay, then it says, for each of the following two possible occurrences, say whether this could have caused the error or not. So they really like this also on the AP test. So the first one, the flask was incompletely flushed with carbon dioxide, resulting in some dry air remaining in the flask. So you had some air instead of carbon dioxide. So air is 80% nitrogen and 20% oxygen. So nitrogen is, the oxygen is the same, but nitrogen is bigger than carbon. So would that cause this problem? Yes, it would. And that's why. Okay? Yes, it would. Okay, next occurrence is the temperature of the air was 23 degrees Celsius, but the temperature of the CO2 was lower than reported. So this is no, this would not work because colder air is more dense, not less. See, instead of being, it was 40 when it should have been 44, this would have taken it the other way. Can you sort of imagine that? If not, just think about it, you'll get it. Okay. Describe the steps in the laboratory method that the student could have used to verify the volume before he got started. Okay, so he should have weighed it. He also could have verified the volume on the flask too. And so how do we get volume usually in the lab? What do you have in your drawer for getting volume? Don't say beaker, it's not precise enough. What do I tell you to always get? When I give you chemicals, there's one over there on the lab table. I tell you, go get your graduated cylinder and bring it to me, right? So what he could have done is he could have filled it with water and then poured it into a graduated cylinder. Okay. Look how fast we did that. Did it kind of make sense? Kind of see how these problems work? So that's how the freedom response usually works. Just like the ones you've already done. You've done two already. Okay, so now we're going to the other notes, back to the regular notes. And we go to the kinetic molecular theory of gases. You learned it in honors already, so this is easy. This is a review. We're just going to apply these little graphs to it. We're going to learn something new with the graphs, but the kinetic molecular theory, you already know. All right, let's go on. Okay, let's see if y'all know this. Gas molecules are in constant random motion. You remembering this? Oops, gotta write it. Gotta draw, not erase. The combined gas volume, and when you do your math, you don't worry about it, right? So they say that is negligible. That means it's so little, it won't affect the math. So we get to ignore it. Okay, that's what that word means. Attraction repulsion forces are negligible. Oops, I put too many. You got too carried away writing that. Oops. Negligible. That means we don't worry about it when we do our gas law math. Collisions bounce off of each other perfectly. What's that word? Starts with an E. You know what? It's like a rubber band. It's elastic, right. So the collisions are thought to be perfectly elastic. And the average kinetic energy does not change. Remember, triangle means change. The average kinetic energy is proportional. Do y'all remember the math symbol for proportional? It's like an equal stuck on a circle. They're proportional, so absolute to the absolute temperature, and that means that the same temperature, all gases have the same average kinetic energy. Now, in that flask, there's going to be some gas molecules moving fast, some of them will be moving slow, but the average speed will be the same for that temperature. Can you imagine that? What controls that speed is temperature. All right, so here's the diagram of the book, the diagram, it's in your book. It shows the distribution of molecular speeds for nitrogen gas at two different temperatures. So when it heated up, notice it's going faster, and also the curve flattens out a little bit. So you don't have as much of maybe a range of the fraction of the molecules going that speed. It flattens out a little bit as you heat it up, okay? True or false? At a given temperature, each molecule in a gas sample is moving at the exact same speed. True or false? I just told y'all. It's false. It is false. Remember, some are going fast, some are going slow, but the average is the same. Okay? True or false? As the temperature of the gas sample increased, the average speed of the gas molecule increases. True or false? True, yes, that's exactly what I told you. True or false? The distribution curve tends to broaden as the temperature is increased, indicating that the range of molecular speeds increases at high temperatures. That's false, it's the opposite. The range is more, as it heats up, it gets flatter, meaning the range is less. Can you see that on the graph? All right, moving right along. What does the diagram below tell us about the relationship between molecular speed and molar mass? So in our first graph, it was all the same gas, just different temperatures. Now we have the same temperature, different speeds depending on the gas, okay? So we're looking at, oh, I skipped something. I skipped the bottom there, didn't I? Yep. All right. Back to the bottom of the page. The average kinetic energy per molecule of a gas is equal to 1/2 mv squared. You learned that in 8th grade honors physical science when you learned the formulas for potential energy and kinetic energy, right? You remember that? Very good. So it's the same formula. This information helps us compare the average speeds at a gas for a given temperature. How should these be arranged in order? Now, lighter particles travel at faster average speeds. So that's important. Everybody remember that on the AP test. So which one is going to be the heaviest of these? Nitrogen, neon, or carbon dioxide? Which one's the heaviest? Well, we can add it up off of the periodic table, can't we? 1 carbon is 12, plus 2 oxygens, 16 each. So that is 32 plus 12, that's 44, right? If my mental math is correct. So that one's 44, okay? Neon, that one's easy. I don't have to add, it's 20. And nitrogen is 14 times 2, that's 28. Okay, so who's the biggest? Who's going to be big and slow? Carbon dioxide. Who's medium? Who's medium? Nitrogen at 28. And who's the smallest and fastest? Neon at 20. That's an easy problem. AP loves this. They like comparing stuff because it is showing that you understand the concept and can apply it. It's a little higher order thinking there. All right. So here we've got that same one. So which one is bigger? Hydrogen or oxygen? Which one's more massive, hydrogen or oxygen? Oxygen, right? So which one is faster, hydrogen or oxygen? Hydrogen is faster. Oxygen is slower. For gases, there is an inverse relationship between molar mass and average molecular speed. So when one goes up, the other one goes down. Mass goes up, speed goes down. You know, that's a lot of times true for people too. Get too much mass, you're not going to be speedy. All right, real gases, deviation from ideal. That is 3.6, the last one we're going to do today. Now, real gases are not ideal. Real gases could have the things that we said were negligible, sometimes they're not, and we need to know when they're not. So gases tend to experience the largest deviation. That means the largest, we're not allowed to say negligible, from the ideal behavior under the conditions of high pressure and low temperature. And this is because of the attractive forces, the F-O-R-C-E-S, looks like farces, the forces. So our intermolecular forces, our IMFs, start playing into it. The particles of an ideal gas are assumed to occupy no space. Now, of course, that's crazy. All matter occupies space and have no attractive forces, but they can actually have some. And however, the particles of a real gas, of course, have volume, and they can have attractive forces. Now, why? Why pressure and volume are the things that are going to make it have that, okay? So look at this. Here I have a gas at one volume, and I have it squished down to a little volume. Notice how now the gas molecules are taking up a lot more of the space. They're getting shoved together, and they can start interacting. Does that make sense to you? So under high pressure, the combined volume is no longer negligible. Okay, good there? Can I scroll? Good. Okay. Explain why, under conditions of low temperature, the pressure of a gas tends to be slightly smaller than the value predicted by the ideal gas law. Okay? The molecules start to move slower. And they have attractive, so then their attractive forces can be in contact longer. And then they can start to stick together, and they won't collide with the walls of the container as much. And that's where pressure comes from, is how much they collide with the walls of the container. They're colliding with each other instead of the walls. They're not hitting the walls as hard. In general, gases tend to experience larger deviations from ideal as the strength of their intermolecular attractive forces increase. For this reason, which of the following molecules is more likely to show a deviation from ideal, hydrogen or water? And then justify your answer. So this is a good practice for an AP question, because we could say, hydrogen's smaller, water's bigger, we're done. But we won't get all the points. So when we have these, over-explain things, okay? So what we can say is, first of all, is hydrogen gas polar or nonpolar? Nonpolar. Oxygen, water is polar. So that's one thing I would write down. The next thing I would say is, what forces does this nonpolar hydrogen gas have? Which intermolecular forces? Does it have hydrogen bonding? No, it's not Teflon. Does it have dipole-dipole? No, it's not polar. So what does it have? It only has London dispersion forces. Only LDF. So we can say that. Only. In our little essay we're going to write. Okay? What about water? What is its big force that it has? It's got LDF It's got dipole, because it is polar. And it's got hydrogen bonds. So way more of these intermolecular forces. You see that we could talk about that? Next, we're going to talk about size. Remember, bigger electron clouds are more squishable, more scootable, and you have more of these forces. So we're going to say this one is smaller, and we're going to say that this one is bigger electron clouds. Okay? And then we're going to, remember our buzzwords, we like to throw them in. This one is less, so we can say therefore, oh, we like therefores, they're good to put in there. Therefore, it is less polarizable. Therefore, this one is more polarizable. And then we would say something that these factors result in water having more deviation from ideal. Okay? Do you see how we stretched out something that was kind of easy into a big fat essay? A lot of college and AP, you have to stretch things out. When I was in college, one time I had to go to a symposium where someone was presenting their research, and it was a guy talking, he had done research with lobsters in Maine. And you could have summed up all of his research that big lobsters go far, little lobsters stay where they are. But I had to write a 4-page typed paper on this. I had to stretch out big lobsters go far, little lobsters stay where they are to 4 pages for a grade. So what did I do? I stated what his research was. I stated what he found. I put his graphs in there. I interpreted his graphs just like he did. And then I had a glorious conclusion. Big lobsters go far, little lobsters stay where they are. Got 100, got an A in the class, okay? But honestly, that is all that paper said. But you gotta learn how to fluff it out. All right, so that's it. We're gonna end the video. Science is great.